All right, welcome back, everybody. Today we're going to talk about Calc Lesson number 4, and this is how you would evaluate limits algebraically using trig and something called the squeeze theorem. So to this point, we have learned a bunch of different algebraic techniques that you might need to learn in order to calculate a limit. No matter what, though, direct substitution is always your first try. And it turns out that when it comes to trig, direct substitution will work so long as the value that you're looking at, which is called the c, is a real number in the domain of a given function. So again, bottom line, direct substitution, even if there is trig involved, is always your first line of defense. If you take a look over here on the right-hand side, these are a bunch of common trig relationships that you're going to be needing for this section, and really you'll need at various points throughout the year. So there is a big trig reference sheet that your teachers have put together. There should be a copy in your class notebook, so I don't know how much you actually have to write down, since you can just go back and reference it at any time. But a quick reminder, on the top left, you have your reciprocal identities. The cotangent goes with the tangent, the cosecant with the sine, and the secant with the cosine. Top right, you have the quotient identities. A tangent is a sine over a cotangent is a cos over a sine. And then in the bottom, you have your three Pythagorean identities. And remember, those work for squares only, no other exponent. So in addition to those formulas you need to remember, you also need to remember the values of the unit circle, not only the degrees and radians, 30, pi over 6, pi over 4, etc., but also the ordered pairs. Those are all on this screen here for you as a reminder. Again, no need to really rush to copy them down. They're also going to be found on that trig reference sheet. And then, of course, over on the right-hand side here, it reminds you that when it comes to something that is specifically on the unit circle, which means that the radius is 1, you don't actually need the more complicated ratios, because the cosine is always the x, the sine is always the y, the tangent is always the y over x. And then these three guys on the right are always the reciprocal of these three guys on the left. So you simply do 1 over or switch the x and the y. All right, so over here in the bottom left-hand or bottom right-hand corner, I have for you just the first quadrants and, of course, the quadrantal. So 1, 0 would be at 0, 0, 1 at pi over 2, pi, 3 pi over 2, and then all the way back around. So let's go ahead and take a look at these 4 easy trig limits. So again, if there's no complicated work involved, you're going to try by just plugging in the value using direct substitution. So for the first one, the limit as x goes to 0 of the tangent of 0, we're simply going to plug in 0, which is going to give us the tangent of 0. In order to calculate the tangent of 0, you're going to go to 0 degrees. You're going to look at the ordered pair, 1, 0. You would look at your trig reference sheet, which tells you that a tangent is equal to a sine over a cosine. So if you put the y value, 0, over the x value, 1, 0 divided by anything is 0, which means the limit of the tangent of x as x goes to 0 is 0. For the top right, the limit as x goes to pi of x cosine of x, again, you're going to try to just plug in a pi everywhere there's an x. So pi is just a pi. To find the cosine of pi, you would go over to where pi is located. The cosine is, of course, the x value. So the x value of that ordered pair is -1. -1 times pi is -pi. So again, don't be scared by the trig. All you're going to try to do at first is simply use direct substitution. And again, sometimes you're going to get lucky. So the limit as x goes to 0 of the sine squared of x, the first thing I want you to realize is that this is really saying the limit as x goes to 0 of the sine of x squared. That's what sine squared of x actually means. So again, you're going to go ahead and try to see if you can just plug in 0. So the sine of 0 squared. In order to find the sine of 0, you would again go back to where 0 degrees is located, or 0 radians, same thing. The sine is the y value, which would be 0. If you go ahead and plug 0 in for the sine of 0, you get 0 squared, which of course everybody knows to be 0. Finally, the limit as x goes to pi over 2 of the cosecant of x, you would hopefully remember that the cosecant is equal to 1 over the sine. You then, of course, would try direct substitution. So this would give you 1 over the sine of pi over 2. In order to find the sine of pi over 2, you have to go to where pi over 2 is located, which is at the top of the circle. The sine is, of course, the y value. If you're doing 1 over the sine of pi over 2, you're doing 1 over 1. And of course, 1 over 1 is equal to 1. So these are about as easy as it gets. The first thing you're always going to try as your first line of defense in the limit war is to go ahead and make sure that you try direct substitution. And again, sometimes you're going to get lucky. What if you don't get lucky and simply plugging in direct substitution doesn't work? Well, then there's a bunch of different maneuvers that you can try, all of which are algebra based. There is something called the squeeze theorem, and the squeeze theorem is something that helps us to calculate more complicated trig limits. As far as what you have to know about the squeeze theorem, what you have to be able to explain about it, the truth is not much. You just have to be able to understand that it's a thing, and as a result of this theorem, there are two very important limits that we can find. So basically what the squeeze theorem says in general is that if you have a function that is being squeezed between two other functions, basically where the f would be located, if you're not able to find the limit of f on its own, if it's being squeezed between the g and the h, you can go ahead and conclude that the limit of f is the same as the limit of the other two. So here it is a little more formally, and just so you know, the squeeze theorem is sometimes called the sandwich theorem or the pinching theorem. Just in case you're at a party this weekend and everyone's talking about the sandwich theorem, I don't want you to look stupid if you don't know what that is, so make sure you know they are the same thing. Again, here is the official long-winded definition. You're not going to have to define it. You just kind of have to know that the squeeze theorem is a thing. We can read all those fancy words, but again, all we're really saying is this. If you have a function that has a difficult limit or one that's undefined, as long as it's being squeezed between two other functions for which you can find the limit, you can go ahead and conclude that they're all the same. So at the left here, you have x squared and negative x squared. Those are two very easy limits to find. In between them, you have a very complicated limit, one that oscillates, in fact. The good news, though, is because that blue function is being squeezed between the other two, we would actually be able to find the limit using the graph, even if we weren't able to do it algebraically. Similarly, over here on the right, let's say that g was a very complicated function we were not able to find the limit of. As long as it was being squeezed between the other two, we would safely be able to go ahead and determine that limit anyway. Again, all you really have to know at the end of the day are the following two formulas. So if you write down nothing else today, it should certainly be those two important special trig limits. So here's the first one. The first one says the limit as x goes to 0 of the sine of x over x is always going to be equal to 1. The second one says that the limit as x goes to 0 of 1 minus the cosine of x over x is always going to be equal to 0. So again, these are direct results of the squeeze theorem. So as long as you know that these two formulas exist, that's really all you need to know. But there are a couple of qualifiers that have to be true in order for you to utilize these. So I've listed them here for you. First of all, it only works if they have the same x. So what that means is that if this is a 1x and this is a 1x, then the formula is true. If this is a 30x and this is also a 30x, then the formula is true. No matter what they are, as long as they are the same, then the formula works. Secondly, you have to make sure that inside of the sine and inside of the cosine, those have to be untouchable. So what that means is that if there was a 10x here, you could not factor that 10 out. You could not divide by 10. Whatever is inside of the sine or cosine has to be untouchable. And then maybe the most important thing, this is only true when x goes to 0. So if it's anything other than 0, it doesn't work. Not that we're really going to try to trick you and make it anything other than 0, but please just be on the lookout and know that it is in fact only true for 0. So we're going to do a bunch of examples now together. I would certainly make sure you have those two special trig limits written down. And if you have any questions for your teacher, now would be a great time to ask. And then again, before we dive into it, most of the work that you're going to do is algebra based. So I wanted to give you a bunch of reminders here, most of which might seem common sense, but never hurts to review. When it comes to problems like this, you're mostly going to be separating things as opposed to putting them together. So here in the first bullet, I just want to remind you that x squared can be rewritten as x times x. Normally, you multiply x times x to get x squared, but really for the majority of these problems, you're going to be going the other way. Similarly here for the second bullet, the sine squared of x can be written as the sine times the sine. 1 minus cosine, the whole thing squared, can be rewritten as two different copies. A tangent is equal to a sine over a cos, so it follows that a tangent squared would be equal to a sine squared over a cosine squared. And then finally, the last one is just a simple breakup using algebra. Sine times cos over x squared. You can absolutely break that up into a sine of x over x times a cosine of x over x. So long as whatever you break it up to be, if it were to multiply back to be the original problem, then it's perfectly legal. So again, these might seem common sense, but if not, doesn't hurt to review them, and certainly wouldn't hurt to write them down if you're watching this on your own or if your teacher gives you the time to. So now let's go ahead and see these problems in practice. And again, I have at the bottom right hand of the screen there the reminders of the important formula. So these are the goals. We want to somehow break it up into as many of these special trig limits as possible, because once we do, we're able to just go ahead and utilize those formulas. So let's say you have the limit as x goes to 0 of the tangent of x over x. You would, of course, try to just plug in 0, but unfortunately, that's going to give you 0 over 0. Remember, that is called the indeterminate form, which means that it's no good. So we have to go ahead and try to do some algebra. So what I'm going to do here is I'm going to take my tangent, and I'm going to rewrite that as the sine over the cosine. And this is all still over x over 1. And again, the reason why I know the tangent is equal to the sine over the cosine, I would just refer to my handy trig reference sheet. Again, this is called the complex fraction. We don't really like those, so we're going to go ahead and rewrite this as the sine over the cos. We're going to multiply by the reciprocal, which would then be sine over cos times 1 over x. In order to create one of these special trig limits, I'm going to just use a rule of algebra, which says I can rearrange this. So I'm going to rearrange to put the sine of x over x, and then I'm going to put 1 over cosine. So again, as long as that would multiply back out to be the original problem, that's why I'm allowed to do that. Now, if I actually go ahead and apply the limit, my limit statement really should be there all the way through, but if you get a little lazy and just leave it to the end, that's fine. Just don't actually forget to do it. So the limit as x goes to 0 of the sine of x over x, that's a 1. That's good news. That's what I was hoping for. Then I have to go ahead and actually take the limit of 1 over the cosine of x, which becomes 1 over the cosine of 0. If I were to refer to my trig reference sheet, the cosine of 0 is 1. So this would be 1 times 1 over 1. And the entire limit would just turn out to be a 1. So again, just to kind of reiterate what it is we're trying to do here, we're trying to do a bunch of algebraic maneuvers that give us as many special trig limits as possible. And then we're going to try to see if we can get it down to a final answer. So here in the second one, we have the limit as x goes to 0 of the 2 tangent of x over x cosine of x. So the first thing I'm going to do is I'm going to take the 2. I'm going to rewrite the tangent as the sine over the cosine. That would be a numerator and a denominator. That would leave the x cosine of x also in the denominator. So from here, again, I'm going to try to rearrange it algebraically to try to get as many special trig formulas as I can. So I'm going to leave the 2 out front. I'm going to replace it. So it's the sine of x over the x. So there's my 2. There's my sine x over x. And that's going to give me 1 over the cosine of x squared. So from here, I'm going to actually go ahead now and find the limit. So when I go and find the limit, the 2 stays a 2. The sine as x goes to 0, or the limit as x goes to 0 of sine of x over x is equal to 1. Actually go ahead and plug in the cosine of 0. So this would be 1 over the cosine of 0 squared. Again, as a reminder, sorry, I'm kind of running out of room here. So 2 times 1 would be 2. The cosine of 0 is again 1. 1 squared is 1, which means this ultimately winds up being 2 times 1, which means the limit of the entire answer turns out to be 2. Let's try some others. So here, the limit as x goes to 0 of the sine of 4x over x. And again, just as a spoiler alert, for these more complicated problems, if you were to try to plug in 0, you would always get 0 over 0. So you technically should test it first. But since I know they're all going to be 0 over 0, I'm not showing that step. So for a problem like this, if you remember what some of my reminders were, the fact that this is a 4x and this is an x means I can't immediately use the formula. They have to be the same in order for the formula to work. Additionally, the 4 that is inside of the sign, I cannot touch that 4. So I can't divide it away. I can't factor it. I can't do any of that. Here's what I can do. I'm going to multiply this entire problem by 4 over 4. Why am I allowed to do that? Well, I'm allowed to do that because 4 over 4, of course, equals 1. Why do I want to do that? Well, if I go ahead and multiply that, I'm going to get 4 sine of 4x over 4x. If I do that, now that I have the sine of 4x over 4x, I am allowed to use this formula because, again, as long as those x quantities are the same, that's going to equal a 1. So 4 times 1 gives me a limit of 4. Similarly, in the bottom one, again, that 2 that is inside the sign, I am not allowed to do anything to that. So I have to think to myself, what is it that I want to do instead? Well, first, I'm going to take this 5, and I'm going to realize it's really a 1/5, and I'm going to factor that 1/5 out. That's then going to leave me with the sine of 2x. Then I'm going to multiply this entire problem by 2 over 2. I'm sorry, I lost my x there. So again, the 5 in the denominator, there's really a 1 up top, so that's 1/5. Then I'm going to take my sine of 2x. I'm going to take the x from the bottom. That gives me this quantity here. And then I'm going to multiply by 2 over 2. Again, 2 over 2 is really a quantity of 1, so that's why I'm allowed to do it. If I go ahead and do a little bit of rearranging now, this 2 and this 1 become a 2 over 5, so 2/5. Then I have the sine of 2x on top, and I'm going to put this 2 and this x together on the bottom. That actually is very good news because the sine of 2x over 2x, as long as they're the same, that becomes a 1. So 2/5 times 1 means my final answer to this problem turns out to be 2/5. Sorry, I probably should have left myself a little bit more room on the screen here. All right, 2 more problems here. So again, if I were to plug in 0, I'm going to get 0 over 0 every time. So I have to go ahead and do some algebraic maneuvers. In the first one here, the fact that I have an addition sign here means I can break this up into 4x squared over x squared plus 3x sine x over x squared. Then I'm going to go ahead and do a little bit of reducing. So 4x squared over x squared, you can go ahead and reduce those x squareds. That becomes a 4. Then you can go ahead and reduce a pair of x's also from the second quantity. So if I reduce a pair of x's from the second quantity, I'm going to get 3 times the sine of x over x. That's amazing. Once I've actually gone ahead and simplified, now I'm actually going to take my limit. Again, I really should be carrying that limit statement down with me the whole time, but I'm a little bit lazy on the computer here. So as long as you take the limit in the end, that's good. The sine of x over x, that's a 1. The limit of 4 is 4. The limit of 3 times 1 is 3. And then the limit of 4 plus 3, that's a 7. You might be wondering, well, why haven't we used the second formula yet? Well, we're going to now. Just for some reason, you don't wind up using the second one as much. I think because of the fact that it always turns out to be 0, those are kind of lame, and there's somehow ways to get the right answer while doing the wrong work. So that's why you don't see that one as much. Here for 6 minus 6 cosine of x over x, looking at the formula, the problem is that there's a big fat 6 there. We wish that there wasn't. So we're going to go ahead and factor that 6 out. If we factor that 6 out, we wind up with 1 minus cosine of x over x. That's the dream. According to our second formula here, the limit of this entire thing is going to be 0. So the answer to this problem is 6 times 0, which of course winds up being 0. So again, your mission after direct substitution is to try to do as much algebra as you can to get down to one or more of these special trig limits. Last 2 problems coming up, and this is where that idea of being able to separate the function really comes in. So the limit as x goes to 0 of sine cubed of x over 2x cubed, I am allowed to break this up into a sine of x over 2x times sine of x over 2x times sine of x over 2x. The reason why that's allowed is because if I was to multiply that whole thing back through, I would get sine cubed on top and then 2x cubed on the bottom. So from here, anytime there's a sine of x over x, that's equal to a 1. The fact that there are all these 2's in the denominators, don't forget that there's a 1 for the top of each of them. So this actually winds up being a 1/2 times a 1/2 times a 1/2, because again, each of these sine of x's over x's turn out to be 1s. So a half times a half times a half gives you a limit of 1/8. And the final problem, very similar. You're going to go ahead and break this up, but turns out you don't have enough x's to go around. So you're going to break this up into sine of x over x times sine of x over x times sine of x over 1. So don't get greedy. You don't have enough to go around. Each of the sine x over x's is going to become a 1. So this is a 1 and this is a 1. So far I have 1 times 1. Then for the lonely sine by itself, you have to actually plug in the 0. Remember, that's what it means to take the limit. So you're going to go ahead and find the sine of 0. If you then take a look at your trig reference sheet, the sine of 0 is 0, which means you're going to wind up with 1 times 0, which is why the final answer to this problem turns out to be 0. So here is homework number 4. Homework number 4 is still in section 1.3. You're going to do 63 to 71 and 73. As always, the answer key is posted and the homework is reviewed daily, but not collected till the end. So make sure that you don't fall behind. Thanks very much for tuning in, and we will catch you next time.